Greetings everyone, I'll be presenting the first problem in the second assignment during lockdown, which is based on section 3.4 that talks about cyclic groups. As we can see, the question says, let AX be elements in a group G. Prove that AX is equal to XA if and only if XA inverse is equal to A inverse times X. Here, we are required to prove that if this is true, then this must be correct, and if this is true, then this must be correct, which is vice versa. Here, we're going to have two proofs. Here, the solution for the first one. Suppose AX is equal to XA. Then, we're going to take one side from this equation. Then we have A inverse times X is equal to A inverse times X times E. Since E is the identity element, and anything times an identity element is equal to itself, then we have A inverse times X is equal to A inverse times X times A inverse. Since E is equal to A times A inverse, A inverse times X is equal to A inverse into X times A inverse. Then we have A inverse times X is equal to A inverse into A times X times A inverse by commutativity. Remember that in our previous chapter, we learned about binary operation, which talks about commutative and associative. We say elements are commutative if AX is equal to XA. And remember that in our first step, we said, let's suppose AX is equal to XA. And then we have used that step here. Then we have A inverse times X is equal to into A inverse times A times X times A inverse. And we have A inverse times X is equal to E times X times A inverse. Since E is equal to A times A inverse, which is the same as A inverse times A, then we have A inverse times X is equal to X times A inverse, since E is the identity element. And we know that anything times an identity element is equal to itself. Thus, we have proved that A inverse times X is the same as X times A inverse. Hence, AX is equal to XA. Then we're going to do the second proof, which is conversely. Suppose A inverse times X is the same as X times A inverse. Then we're going to take one side from this equation. AX is equal to AX times E, since E is the identity element. Then we have AX is equal to A times X times A inverse times A. Since E is equal to A inverse times A, then we have AX is equal to A into X times A inverse times A. AX is equal to A into A inverse times X times A by commutativity. And we say things are commutative if A inverse times X is the same as X times A inverse. And remember that in our first step, we said that suppose A inverse times x is the same as x times A inverse. Then we have AX is equal to into A times A inverse times x times A. AX is equal to E times x times A. Since E is equal to A times A inverse, AX is equal to x times A. Since E is the multiplicative identity element, and anything times an identity element is equal to itself. Thus, we have proved that AX is the same as XA. Hence, A inverse times x is the same as x times A inverse. Then we are done with second proof. Hope you guys will understand.
Hi everyone, I'm Namza Mozulu from group 4. Okay. Let A be an element of a group G, then we have to prove that C of A is a subgroup of G. Okay. Firstly, we have to know the definition of a center of a group. Okay. Solution. Then the definition of a center of a group in this problem is C of A is equal to X is an element of G such that X times A is equal to A times X for all A is an element of G. Okay, in order for C of A to be a subgroup of G, it must satisfy certain conditions, namely it must contain inverses, it must have an identity element, it must be closed, and it must be non-empty. So here actually we are proving that C of A satisfies these conditions. Now let's suppose we have C of A is a subgroup of G, then C of A is a non-empty since E times A is equal to A times E such that E is an element of A. Then we let xy be an element of A using the associative property and the definition of a center of a group. So we have for all A is an element of G such that into xy times A is equal to x into AY is equal to into XA times Y is equal to into AX times Y equals to A into XY. Then which implies that into XY is equal into XY times A is equal to A into XY, and then in this way you have XY is an element of C of A, and then from here we have C of A that is closed, which satisfies the first condition. And then now let's suppose we have X inverse is an element of C of A, then we have X inverse times A is equal to X inverse times A into E, since E is a multiplicative identity element. And then we have X inverse times A is equal to X inverse times A into X times X inverse, since E is equal to X times X inverse. Then we are having X inverse times A is equal to X inverse into A times X inverse, and then we have X inverse times A is equal to X inverse into A times x inverse by definition of a center of a group, which implies that a times x is equal to x times a. Then we are having inverse. X inverse times a is equal to into x inverse times x times a times x inverse. X inverse times equals to e times a times x inverse. Then we have x inverse times a is equal to a times x inverse, since e is a multiplicative identity element. Then from here, x inverse is an element of a. Then we have from here we have c of a that contains inverses. Then a, and then from here we should see that this element satisfies all these conditions, and then therefore C of A is a subgroup of G. Thank you.
Hello, I'm also Dlamini. I'm from Group 4. My presentation will be based on the two problems. Firstly, solving the equation by finding the inverse of the congruent class. Then the second problem will be finding the generators of modulo 22. For the first problem, the equation given is congruent class of 4 times the congruent class of x, which is equal to the congruent class of 5 in modulo 13. Then the solution, when we start with this, we'll just say congruent class of 4 times the congruent class of x is equal to the congruent class of 5. Then that means or implies that the congruent class of x is given by the inverse of the congruent class of 4 times the congruent of 5. Now we'll have to find the value or the multiplicative inverse of 4 in modulo 13. To do that, we'll use a Euclidean algorithm. We'll say 13 is equal to 4, and we'll ask ourselves 4 goes into 13 3 times, then the remainder is 1. Therefore we can conclude that 1 is equal to 13 into 1 plus 4 times into minus 3. Then we put it in the standard form, of which is 4 into minus 3 is congruent to 1 modulo 13. With this, we can now conclude that the inverse of the congruent class of 4 is equal to the congruent class of negative 3. Adding a 13, since it's a negative, we can't have a congruent class which is negative. We'll have the congruent class of 10. Since the congruent class of x was given by the inverse of the congruent class of 4 times the congruent class of 5, and we now know the value, the exact value of the congruent class of the inverse of 4, we can just substitute that. So it's going to be congruent class of x equal to the congruent class of 10 times the congruent class of 5. Then our congruent class of x is equal to the congruent class of 50. Then the next step will be finding the remainder when 50 is divided by 13. Again, using the Euclidean algorithm, we'll say it's 50 is equal to 13, and we ask 13 goes 3 times into 50 plus 11 as a remainder. Therefore, our congruent class of x is equal to the congruent class of 11. That is it for the first part. Find all the generators of Z22. What are the generators? A generator is an element that generates all elements in a group. So generators of Z22 are all the elements in which the greatest common divisor with 22 is 1. Hence, the generators of Z22 will be all the positive numbers that are less than 22 and co-prime to 22. Those are the congruent class of 1, the congruent class of 3, the congruent class of 5, the congruent class of 7, the congruent class of 9, the congruent class of 11, the congruent class of 13, the congruent class of 15, 17, 19, and lastly the congruent class of 21.
Good morning, everyone. My name is Nolbabalo Sachu and my student number is 2018-22-113. I'm going to present assignment 2, exercise 2.6, number 11 from the book. And the question says that solve the system of equations in modulo 7. And we are given two equations. The first equation we'll call it equation 1 and the second equation we'll call it equation 2. We can eliminate the congruence class of x by subtracting equation 1 from equation 2. And this is what we get. The congruence class of 3 times the congruence class of y, which is equals to the congruence class of 1. And we call this equation 3. We can find a multiplicative inverse of the congruence class of 3 in modulo 7 by using the Euclidean algorithm. We start by writing the bigger number, which is 7, and 3 goes to 7 2 times, and the remainder is 1. And this is how we write it. 7 is equals to 3 times 2, which is a quotient, plus 1, which is a remainder. Then we solve for a non-zero remainder, which is 1. 1 is equals to 7 times 1 plus 3 times minus 2. And 3 times minus 2 is congruent to 1 more 7. The inverse of the congruence class of 3 is equals to the congruence class of minus 2, which is equals to the congruence class of 5. And this is how we get the congruence class of 5. We take the congruence class of 2, which is the inverse of the congruence class of 3, plus the congruence class of 7 from modulo 7. And you get the congruence class of 5 by addition property. Then we use this equation, the congruence class of y, which is equal to the inverse of the congruence class of A times the congruence class of B. Then we go back to equation 3 and make the congruence class of y the subject of the formula. And we get the congruence class of y equals to the inverse of the congruence class of 3 times the congruence class of 1. And we know that the inverse of the congruence class of 3 is equal to the congruence class of 5. Then we substitute the inverse of the congruence class of F3 by the congruence class of 5. Therefore, the congruence class of y is equal to the congruence class of 5. Then we solve for the congruence class of x by substituting the congruence class of y, which is equal to the congruence class of 5, into equation 1. And this is equation 1. Then we substitute the congruence class of y by the congruence class of 5. and we transpose the congruence class of 5 to the other side, and this is what we get: the congruence class of 2 times the congruence class of x, which is equal to the congruence class of -1, and we call this equation 4. We can find a multiplicative inverse of the congruence class of 2 in modulo 7 by using the Euclidean algorithm. We start by writing the bigger number, which is 7, and 2 goes to 7 3 times, and the remainder is 1. And this is how we write it: 7 is equal to 2 times 3, which is a quotient, plus the remainder 1. Then we solve for a non-zero remainder, which is 1. 1 is equal to 7 times 1 plus 2 times -3. And 2 times -3 is congruent to 1 mod 7. The inverse of the congruence class of 2 is equal to the congruence class of -3, which is equal to the congruence class of 4. And this is how we get the congruence class of 4. We take the inverse of the congruence class of 2, which is the congruence class of 3. We add it with the congruence class of 7 from modulo 7, and we get the congruence class of 4 by addition property. Then we use this equation, the congruence class of x, which is equal to the inverse of the congruence class of A times the congruence class of B. Then we go back to equation 4 and make the congruence class of x the subject of the formula, and we get the congruence class of x, which is equal to the inverse of the congruence class of 2 times the congruence class of -1. And we know that the congruence class of the inverse of the congruence class of 2 is equal to the congruence class of 4. Then we substitute the inverse of congruence class of 2 by the congruence class of 4, and we get the congruence class of x equals to the congruence class of 4 times the congruence class of -1. And we get the congruence class of x equals to the congruence class of -4. Therefore, the congruence class of x is equal to the congruence class of 3. And this is how we got the congruent class of 3. We take the congruence class of -4, which is the inverse of the congruence class of 2, plus the congruence class of 7 from modulo 7, and we get the congruence class of 3 by addition property. Thank you.
Good morning, everyone. My name is Krishnannair, the group leader of Group 4. I'll be presenting the second assignment that we were given. Without further ado, let's go to my problem. My question wanted me to solve the system of equations in modulo 7. I was giving the common class of 3 into the common class of x plus the common class of 2 into the common class of y equals to the common class of 1, and the following equation, which we can all see. I'm trying to refrain from saying common class before I bite my tongue, so I will simply just label the equations for reference purposes. The first one is equation 1, the second one is equation 2. So I want to create a new equation that has only one unknown variable. So I'm going to eliminate the common class of y from one of the equation, or the combination of the two equations, by subtracting equation 2 from the common class of 3 into equation 1. I'm multiplying by the common class of 3 towards equation 1 because I want to match the value of the common class of 6 into the common class of y with the one above
by multiplying by congruent class of 3, I'm going to get the congruent class of 6 into the congruent class of y as well here. So the computation congruent class of 3 into equation 1 will give me the following equation. I will have 3 and 3 into x, 3 and 2 into y, 3 and which is equal to 3 and 1. 3 and 3 will give me a 9, and 3 and 2 will give me a 6, and 3 and 1 will give me a 3. So that means that my 3 into 1 will give me an equation 9 and x plus 6 and y equal to 3. But I'm looking for the common class of 3 into 1 minus equation 2. Then this computation will give me 9x minus 5x, which will give me a congruent class of y into congruent class of x. And this 6 into y and this 6 into y will give me 0, so I do not need to add it here. And lastly, the congruent class of 3 minus congruent class of 5 will give me the congruent class of minus 2. So I'm looking for the congruent class of x, so I do not need this 4 on this side. I can simply eliminate it by multiplying by the multiplicative inverse both sides. So multiplying by congruent class of 4 inverse both sides, this and this will eliminate, and I'll be left with x, and this side will remain as is. I can label this as equation 3 for reference purposes, and I can now try to find the equivalent value of the multiplicative inverse of 4. So I can do that by solving for the multiplicative inverse using the Euclidean algorithm. I'll simply take the 7, since we're doing our workings on modulo 7. I'll divide the 7 by 4 and find the remainder. So this will give me 7 equals to 4 into 1. That means 4 goes once into 7, and the remainder is 3. I do the same for 4 and 3. 3 goes once into 4, and the remainder is 1. I make the remainders the subjects of the equations. The first one would be 3 equals to 7 into 1 plus 4 into minus 1. I just simply took the 4 to the other side, and 1 equals to 4 into 1 plus 3 into minus 1, and again I took the 3 to the other side, and I get 3 into minus 1. I substitute the remainder 3 into the remainder 1 equation. Substitute the remainders, then I get 1 equals to 4 into 1 plus 4 is 3. I put the equivalence of 3, which is 7 into 1 plus 4 into minus 1, all into minus 1. So the final answer becomes 1 equals to 4 into 2 plus 7 into minus 1. I'm looking for the multiplicative inverse of 4, so I can simply make this for the subject. Make for the subject, and then I will have 4 into 2 equals to 1 plus 7. 1 plus 1 into 7. I simply took this 7 into minus 1 to the other side, and I got this 1 to 7 as positive. So this is the same as 4 into 2 congruent to 1 modulo 7. Remember, a multiplicative inverse for an element, say x, will be the element in which, when you multiply x and that element, you get the multiplicative identity, which is 1. And in this case, 4 and 4 into 2 gives you 1 mod 7, which is the multiplicative identity element. So therefore my multiplicative inverse for 4 is equal to the common class of 2. We substitute this multiplicative inverse into equation 3, and remember equation 3 was common class of x equal to the inverse into the common class of minus 2. We substitute 2 and we get common class of 2 into common class of negative 2. This will give me x equal to minus 4, and I need not leave this. I do not need to leave this in a negative form, so I can add 7 to get a common class of positive 3. I found the first unknown. Now to find the congruent class of y, I have to substitute what I found here into equation 1. So I'm substituting the congruent class of x equal to 3 into equation 1. This will give me congruent class of 3 into 3 plus congruent class of 2 into congruent class of y equals to the congruent class of 1. And this 3 and 3 will give me a 9 plus the congruent class of 2 into congruent class of y equals to 1. I will need to eliminate this common class of 9 by subtracting the common class of 9 both sides. This will give me the common class of 2 into the common class of y equal to common class of 1 minus the common class of 9. Computing this would give me the common class of minus 8. So I do not need this compound form. I only need the congruent class of y, so I can eliminate the 2 by multiplying by its multiplicative identity to get the identity element or the multiplicative identity element. So I'll multiply by the multiplicative inverse both sides. This will eliminate the 2 and I'll have 1, and on this side I'm going to get the multiplicative inverse of 2 into the common class of minus 8, and I can call this my equation 4. I can then find the multiplicative inverse of 2 in modulo 7 by simply dividing by 7 by 2 and finding its remainders. So I know that 2 goes 3 times into 7 and the remainder is 1. Once I find the remainder of 1, I can stop and just simply make my 3 into 2 my subject of this equation. This will give me 2 into minus 3 equals to 1 plus minus 7 into minus 1 into 7. I simply took this 3 into 2 to the other side and this 7 into the other side, and that's why we have these negative signs. And finally, this is equivalent to 2 into 3 congruent to 1 mod 7, or this implies that 2 into minus 3 is equivalent to 1 mod 7. And remember again about the multiplicative inverse. We said the multiplicative inverse is the element in which, when we multiply that element in question, we get an multiplicative identity element of 1, and in this case when we multiply 2 and 3 we get 1 mod 7, which is the multiplicative identity element. Therefore the multiplicative inverse for 2 will be equal to the common class of minus 3, but I do not need to leave this as negative 3. I'll just simply add 7 to get a positive 4, and this is equivalent to the multiplicative inverse of minus 2.
Yes.
And then we can substitute the multiplicative inverse of 2 into equation 4. Remember, equation 4 was the common class of y equal to the multiplicative inverse of 2 into the common class of minus 8. So instead of the inverse, we substitute congruent class of 4, and this would give us a congruent class of 4 equal to 4 into 8, and this would give us the congruent class of minus 32, and we are looking for a positive number, or the smallest positive number. So we can keep on adding 7 until we get the first positive number, and that first positive number will be our answer. So if we keep on adding 7, we're going to end up getting 3. Therefore the congruent class of y is equal to 3, and that solves our second unknown. We found all the unknown variables. We have solved the the systems of equations. Thank you for tuning in.